Hello. This is the first in a series of presentations about hyperbolic functions. There's quite a lot of material to cover, so we'll start small today and look at where hyperbolic functions come from, their definitions, how to generate the sort of identities that exist for the circular functions, sine and cosine, and an example. We start by asking a question. What is the sine and cosine of ix, where x is real and I is the square root of -1? To answer this, we use Euler's formula. E to the ix equals cos x plus I sine x. Replacing x by minus x gives e to the minus x equals cos x minus I sine x. Adding equations 1 and 2 and dividing by 2 gives cos x equals e to the ix plus e to the minus ix on 2. And similarly, subtracting and dividing by 2i gives sine x equals e to the ix minus e to the minus ix on 2i. Now we replace x by ix in equation 3 to give cos ix equals e to the I squared x plus e to the minus I squared x on 2, and this simplifies to e to the x plus e to the minus x on 2. This tells us that the cosine of an imaginary number is real. Replacing x by ix in 4 gives sine ix equals e to the I squared x minus e to the minus I squared x on 2i, and that simplifies to I into e to the x minus e to the minus x on 2. This tells us that the sign of an imaginary number is imaginary. Well, the expressions on the right-hand side of equations 5 and 6 are used sufficiently often and are sufficiently useful that they're given names. We define the hyperbolic sine of x, pronounced shine x, as shine x equals e to the x minus e to the minus x on 2. And the hyperbolic cosine of x, cosh x, as cosh x equals e to the x plus e to the minus x on 2. So with these definitions, equation 5 becomes sine ix equals I shine x, and equation 6 becomes cos ix equals cosh x. At this point, we can easily answer the question, what is the shine and cosh of ix? We replace x by ix in equation 7 to get shine ix equals I sine x. And we replace x by ix in equation 8 to give cosh ix equals cos x. We now define the other hyperbolic functions by analogy with the circular functions. Just as cosec is 1 over sine, we define cosec as 1 over shine. Next, as sec is 1 over cos, so is sech 1 over cosh. And we define tan as sine over cos, so similarly we define tanch as shine over cosh. And finally, just as cot is 1 over tan, we have coth as 1 over tanch. Now we're going to look at some hyperbolic identities. The point to remember here is that for every trigonometric circular identity, there's a corresponding hyperbolic identity. We won't go through them all, just derive a few to illustrate the point. For the first example, we'll start with the identity sine squared x plus cos squared x equals 1. Now substitute ix for x. Recall that sine ix equals I shine x and cos ix equals cosh x, and we get the identity cosh squared minus shine squared equals 1. Next, let's look at one of the double angle formulae. We'll take sine 2x equals 2 sine x cos x. Again, we replace x by ix to give sine 2ix equals 2 sine ix cos ix. And that simplifies to shine 2x equals 2 shine x cosh x. For the final example, And remember, this technique works for all of the trigonometric identities. Let's take the addition formula for tan of a plus b. We have tan a plus b equals tan a plus tan b over 1 minus tan a tan b. Now replace a by ia and b by ib, and writing tan as sine over cos, we get sine of I into a plus b over cos of I into a plus b equals sine of ia over cos of ia, etc. Now we replace sine by shine and cos by cosh in the usual way to give I shine a plus b over cosh a plus b equals I shine a over cosh a, etc. Cancelling I from both sides and tidying up gives tanch a plus b equals tanch a plus tanch b over 1 plus tanch a tanch b. Finally, let's do a numerical example. Suppose we wish to evaluate the sine of 2 plus 3i. We know that sine of a plus b equals sine a cos b plus cos a sine b. So we let a equals 2 and b equals 3i to give sine of 2 plus 3i equals sine 2 cos 3i plus cos 2 sine 3i. That simplifies to sine 2 cos 3 plus I cos 2 sine 3, and that simplifies to 9.154 minus 4.169i.